For the remainder of this depression lengthy series of lectures, we're going to be talking about some of the theories about why we have clinical depression. Now, there are more than one theory, and that's as it should be, because it is highly likely that there are more than one reasons that we end up with something like clinical depression. It is very often, you can see like a syndrome. So let us go to our notes and start reviewing some of these various hypotheses. And the first one should not be at all surprising to you, the monoamine hypothesis. Remember back when we first were talking about treatments and the discovery of different aspects of depression, and serotonin, norepinephrine were right up there. And one of the things that has been found in suicidally depressed patients, not your, let's say, average patient with clinical depression, that's probably a bad way of putting it, but is that there is a functional deficiency or depletion of norepinephrine and or serotonin, which can be indicated in part by this major metabolite, 5-HIAA. Forget, you don't need to know the whole regular word title, which is a major metabolite of serotonin. That is significantly decreased in suicidally depressed patients. And for some, that suggests that there's poor impulse control. So is this associated with, okay, you are depressed and suddenly you can't control the impulse and you have enough energy to follow through? In autopsy studies done with such patients, it has been noted that there are certain subtypes, and pay attention to the word subtype because we're going to talk about that in just 1 minute, of norepinephrine and serotonergic receptors that are elevated, upregulated, if you will, in depressed individuals who have not received pharmacological treatment. That is so important because once you have received pharmacological treatment, you have exogenously from outside altered potentially receptor levels, circulating levels of a neurotransmitter. In fact, even the functioning of neighboring neurons and other types of neurons may have been affected. So that's important. And presumably this upregulation in receptors is to compensate for low levels of the particular neurotransmitter, norepinephrine or serotonin. And it goes back to my analogy of if you have, you need to catch 3 balls. You have to do that or else something tragic will happen. And you have a whole baseball field and you only have 4 balls being thrown out. You better have a lot of players, receptors, out in the field to try to catch those very few balls, right? So fewer neurotransmitter molecules or baseballs, more receptors, players, to try to receive those. If you have 100 balls being simultaneously thrown out into the outfield, you only need to make sure you have a couple people out there, receptors, to get 4. Okay, so hopefully that'll help a little bit with the idea of upregulation. Receptor subtypes I mentioned a moment ago are very, very, very important. And we could go on all day with the different types and everything, but for this particular course, I'm going to try to keep it very basic. And what we're going to talk about in the serotonergic system are a couple of different kinds. First, terminal autoreceptors, somatodendritic autoreceptors, and postsynaptic receptors. Now, if you remember back in some of the earlier notes and on the crossword puzzle, in fact, autoreceptor is a receptor that will engage the same kind of neurotransmitter molecule that the neuron it is on is releasing. So we have a neuron releasing serotonin, a receptor that's a 1D receptor, serotonergic 1D, is located on that same neuron, but at the terminals, okay? And that's giving the message. If serotonin engages with one of these terminal autoreceptors, it's signaling that neuron, whoa, there's a lot out there, let's not release anymore right now, okay? Now, when we look at somatodendritic autoreceptors, we're looking at receptors on the serotonergic neuron up on its cell body and or dendrites that are activated by serotonin. So serotonin's flowing around, wow, and here is the neuron that released it, and there are receptors here on the dendrites and on the cell body, and all of a sudden serotonin is activating those, and it's like, whoa, whoa, serotonin, look it, we need to stop what? Firing, because there's plenty out there. We can relax, take a little break here. And then finally, notice this is a 2A. These autoreceptors are both sub 1, excuse me. When this is a postsynaptic regular receptor, excuse me. And that is on the neuron following. I'm going to have to get something, pretty sure, to stop my coughing. And so I'm going to stop the share real quickly. Okay, this is pretty close to class, right? Had to cough, couldn't stop, had to run, get some water, get a drink. Hopefully we'll get through this. Probably the effect of doing way too much of this today. Anyway, apologize. Back to our notes here. Now it's a 5-HT2A. I'm back here. That is not on the same neuron that released the serotonin. It's the next one, postsynaptic, after the synapse. Now, when these are stimulated on this next neuron, it tells that neuron to fire, okay? Hopefully that makes sense to you. Now, all of this is supported by drug protocol. Autoreceptors trigger reduction in serotonin release when there is an increase in extracellular serotonin. Artigas et al., homework, administered a serotonergic autoreceptor blocker called Pindolol, along with an SSRI. And that produced even more extracellular serotonin levels and ultimately antidepressant effects. Because what are we doing? We're promoting more serotonin out in the synapse because you're not allowing it to be taken back up because of this SSRI, but you're also not allowing it to activate an autoreceptor and slow down either the release or the firing, okay? So that's enhances the effect. Okay, what else do we have down here? Abnormality in the function receptors for monoamine neurotransmitters may be another reason. Let me scoot back up here for a minute because I want to make sure you're following along with me. It can be overwhelming and confusing, but we've got more than one way that we could have a problem with these monoamines. Abnormality in the functioning receptors, problems with gene expression, okay? Those are the next two that we're looking at, all right? So it may be that the receptors are not functioning correctly. It may not be that there's not enough serotonin. There may be plenty of serotonin out there, okay? The first theory of monoamine says that there isn't. Here's another one, that the function receptors aren't right. They're abnormal. And they, in fact, can lead to, can be caused by not enough neurotransmitter, but there can be other reasons too. So here, without going into it too much, I have listed, may be itself caused by depletion of neurotransmitters, NTs, may be due to abnormalities of the receptors themselves. There may be some problem, whoa, now we're getting tricky, with signaling of the receptor to other downstream events. And I think, honestly, looking at the delay in the behavioral effects of SSRIs and such, we know that there's probably something else being involved, and it might be downstream. So finally here, we have a third way of looking at this monoamine hypothesis. And if this is confusing for you, hang in there, and I will make sure that we review this before the exam, because it is important that you know this. Hint, hint. Monoamine hypothesis, here's third, of gene expression. We have a deficiency in molecular functioning, perhaps. Now, don't get overwhelmed with the tech speak here. Just let me kind of interpret, if you will, this. It might be that the signal communication from the neuron that's releasing either norepinephrine or serotonin is deficient. So that next neuron that should be firing isn't doing what it should. And one possible candidate, and this is very believable because of some of the studies that have been done, is a flaw in signal transduction, communication and interpretation, okay, in the target gene for BDNF. Hugely important. We will talk about this probably 3 or 4 more times through the rest of the semester. BDNF, brain-derived neurotrophic factor. What does neurotrophic mean? It means producing or more neurons, cells, okay? BDNF normally sustains neurons, it like feeds them and keeps them healthy. But under stress, the gene for BDNF is repressed. You're not getting that gene expression that you should, so you're not getting that positive effect on neurons. So that can lead to possible apoptosis of weakened neurons in the hippocampus, depression, more episodes of depression, and less responsiveness to treatment. And that is something that's important too, because we want our treatments to be effective. And if this is potentially the cause, you're going to be treatment resistant. Now, if you're in my biopsychostress class, especially right now, I've just actually finished a little lecture about the hippocampus and the receptors for glucocorticoids and such. That ties directly in with this. Under stress, you have lots more glucocorticoids being released. And it is possible for this gene to be repressed or reduced. Now you're like, okay, well, that's a nice hypothesis, but what kind of evidence do you have? You see, tricky. Antidepressants have been shown to activate genes for neurotrophic factors, and they're stimulatory. Whoa, this actually might make a little sense. So those are 3 different forms of monoamine hypotheses. So we have the monoamine hypothesis, but there's 3 different ways technically. And forgive me for going back up again, but I just want to make sure. The first being functional deficiency or depletion, that's 1. Scroll down. Abnormality in the functioning receptors, 2. Gene expression, deficiency in molecular functioning, 3. Okay, that's what you're going to need to know. Okay, let's go on to the second big hypothesis. And you'll notice this is in red here, different reasons, some having to do with the partial outlines. So you can put this, if you can change it all to black if you wish, whatever is good for you. Anyway, the neurokinin hypothesis of emotional dysfunction. Now notice it says emotional dysfunction. That is kind of interrelated with the depression. So neurokinins, as neurotransmitter discoveries go, are relatively new. Okay, they've been around for a while, but if you look at the whole history, they're on the newer end. They're peptide neurotransmitters, and it was discovered serendipitously. I love the word serendipitous. Serendipitously. I mean, that is just by sheer something else was going on, and all of a sudden you notice. That is truly how so many of the major scientific findings have actually occurred. Substance P, which is a neurokinin, and it has to do with pain. A substance P antagonist, blocking substance P, had antidepressant effects. Neurokinins are present in areas of the brain that, 1, are critical for regulating emotions, and 2, are rich in monoamines. Okay, so that's showing that you not only have the antidepressant effects, but that this neurokinin can actually interact with receptors in areas of the brain that would be absolutely related to depression. Also, neurokinins may actually specifically modulate that volume transmission of monoamines. Remember how we have that hose squirting neurotransmitters in one place, but we also have those little holes in the hose where there can be sprinkling out volume transmission. Okay, that's why we kind of had to look at that before. So that's second. Third, hypothalamus pituitary adrenal theory of depression. And I've got more of this tacked on to the end of this lecture. I'm actually pretty interested in this whole area of the depression theories. HPA, I'm going to call it HPA from here on in. Depressed individuals synthesize, this is a theory, and release more CRH, corticotropin releasing hormone, from the hypothalamus, and more ACTH as a result, adrenocorticotropic hormone, from the anterior pituitary. And then that leads to more glucocorticoids from the adrenal cortex in response to stress. Okay, this has to happen anyway. I wish I could have all of you have taken biopsychostress before you even take this course, because this would be like, oh, of course. Knowing that that's not true and not possible, probably. CRH from the hypothalamus prompts the release of ACTH from the anterior pituitary, where it's hooked to, which will then tell your adrenal glands, secrete more glucocorticoids, more cortisol, let it out, go. Okay, now that's normal, but in many, not all, but many depressed individuals, they actually have more of this being synthesized and released under stress. So and normals, and this is not my vernacular, it's kind of what's out there. In other words, people who do not have abnormal cortisol, glucocorticoid levels. Cortisol peaks at 8 a.m. in the morning at some point, and then goes down. There's a little peak later, and then it goes down for the rest of the day in the evening. 50% of depressed patients in a couple of studies, some studies where they were really starting to look at this, had high evening levels of cortisol, which means their cortisol was high all the time. Okay. And there's something actually, and I've actually had this test done, dexamethasone suppression test. Dexamethasone is a synthetic glucocorticoid. When you they used to have to give it to you in injections. Now you can take pills of, tablets of dexamethasone. Your body goes, oh, that's cortisol. Your body reads that as your own natural occurring cortisol. And so think about this. Your hypothalamus wants to monitor and adjust the release of all these hormones. And if there is a lot of cortisol circulating and your hypothalamus gets wind of that, it goes, whoa, I do not need to release so much CRH. And the pituitary gland, anterior pituitary, goes, whoa, I'm not getting the message to release ACTH, and thus you're not going to release so much cortisol on your own. That's the negative feedback and response, the negative feedback response. Now, for some depressed individuals, you can keep pumping them through lots of dexamethasone. Just keep pumping it in. And their hypothalamus and pituitary gland do not react to that. They still keep doing their own thing. So you don't have that suppression. In this case, you want suppression because there's plenty out there. We're administering it exogenously from outside of your body. And your hypothalamus, your brain should respond to that like, whoa, there's plenty out there, so let's turn her down. Again, in many people with depression, you don't get that negative feedback response. The problem is this might be the result rather than the cause of depression. Both norepinephrine and serotonin have been shown to modulate the secretion of hormones from the hypothalamus. Maybe not having enough of these monoamines, norepinephrine and serotonin, think about the first theory that we talked about, leads to oversecretion of CRH and other stress hormones. Always have to think about which came first, the horse or the cart, the chicken or the egg, all those good things. Okay, next, fourth, D, diastasis stress model. This is the theory that someone inherits a tendency to develop depression. If you look back at some of the earlier depression notes, we talked about that genetic predisposition, okay? So you might have hypoactive immune systems. In other words, your systems just aren't active enough. You might have hyperactive HPA systems. In other words, you just might genetically be programmed to have HPA axis systems that produce more of the stress hormones and other hormones, by the way. Oh, or you could have, oh no, double whammy, double whammy. You could have both. Oh my gosh. You could have very lazy immune systems. And you could have a hyper excitable, overactive HPA axis. Together, you can understand where you would end up with some different neurotransmitter imbalances. If exposed to stress early in life, systems can become sensitized and overreact to stress. Here is another one of the many reasons I ended up developing a sequel course to this called Neurobiology of Childhood Mental Disorders. With the advent of some of the findings, the research, and our understanding of these systems, it is becoming more and more apparent that early life stress can change brain systems and other systems as well. In early studies, if you looked at rats, and rat babies are called rat pups, if you separate them from their mothers, you have an increase in glucocorticoid levels. And you're like, well, yeah, of course you do. They're stressed. My goodness, you took them away from mom. Oh, but that's not the end of it. These increased glucocorticoid levels persist into adulthood in these little babies. Interestingly enough, it has been found that preemies, and this is human babies, have a higher incidence of depression as adults. Think about preemies and their arrival into the world and some of the things they have to experience. So I'm just going to scroll back for a minute. This diastasis stress model is where we are. Oh boy. And a modern formulation of psychiatric disorders, and when we're talking about this diastasis stress model, involves the integration, combining of at least 4 key elements. 1, genetic vulnerability. Okay, you inherit an abnormal gene, which then causes synthesis of an abnormal or gene product, so on and so forth. This does not seem to fit the vast majority of psychiatric disorders. It does fit like Huntington's disease, but that's not really what we're talking about. But you can have a genetic vulnerability, and that we can talk about in relationship to depression. Second, life event stressors that come the individual's way. So you inherit a vulnerability, but development of the disorder depends on numerous other factors, or even another factor. The second hit hypothesis, so important. Please remember that second hit hypothesis idea. Also, for this particular theory, you have to also take a look at the individual's personality, that individual's coping skills, and social support. Again, wish you all could take biopsychostress because social support plays a huge role. Other environmental influences upon the individual and his genome that include things like viruses, toxins, and various other diseases can also be a factor. So you take all of these 4 components, you mix them up, shake them up into a cocktail, and you have the diastasis stress model of depression. This 2-hit hypothesis, quote, I've got this because this is important for you, states that in order to manifest an overt psychiatric disorder, one must sustain the first hit of a genetic vulnerability and a second hit of some type from the environment. And remember, that can be any type of environmental influence. So let's move on to the next theory of depression, the circadian rhythm hypothesis of depression. And this theory hypothesis states that potentially it's possible that the efficiency in which your rhythms are locked together is impaired. We're supposed to have different physiological rhythms that connect and move together. And this disruption may be caused by either environmental or physiological events. And it's called, for example, sleep and temperature cycles are supposed to be together. Your temperature is supposed to go down as you go to sleep. And before you wake up, your temperature should start rising. When it doesn't work that way, or even opposite, you have a situation where it's called desynchronization. This particular hypothesis says that if you have this desynchronization in some of these physiological rhythms, you can end up with clinical depression. And actually, this particular hypothesis is consistent with a lot of the chemical and physiological abnormalities that we find in individuals who exhibit depression. And it could, and this is important too, could explain the very slow latency of the clinical response to medication. Remember again, the fact that you can start taking, let's say, an SSRI, and immediately there's a difference in the synapse, but not in the depression, not in the behavior, not in the clinical response. Relapse would be expected if this were the case, if continuing environmental factors or stimuli disrupt the rhythms. And one of the very good examples of this are people who are shift workers who have to change what hours they get up and go to sleep and work. So that is also possible. The next theory that we're going to talk about is very different. It's the lack of new cell growth. And I think this is a very interesting theory. We're going to look at the hippocampus for a minute. Remember the structure? Remember where it is in the brain? Associated with memory, also considered part of the limbic system. Is smaller than normal in many depressed patients. Several of the most effective ADs, antidepressants, seem to increase brain cell growth. Wow. Therefore, it's possible that disruptions in the cycle of new cell growth may lead to depression. Here's some evidence that has been reported. Brains of 23 people who suffered from either major depression or bipolar had smaller and less densely packed neurons and fewer glial cells in the prefrontal cortex up here. These changes may be related to the effects of stress, let me move me here, on the brain, because this should sound a little familiar, I hope. Glucocorticoids can disrupt neuronal connections, shrink apart, and cause cell atrophy, dying, just getting all shrunken. Atrophy is shrinking, and death. Also can inhibit cell growth in the brain. Okay, so as you should, you're going, okay, is there any evidence that any of the treatments actually impact brain cell growth? As a matter of fact, I'm glad you asked. Prozac has been shown to increase serotonin release, which then tends to promote brain cell growth, okay? Electroconvulsive therapy also has been shown to encourage brain cell growth, at least in preliminary studies. Lithium, exercise, which leads to increased serotonin release, especially if it is like the very like walking, anything that is very systematic, that can help promote more serotonin release, which then, of course, can potentially encourage brain cell growth. Also, vagal nerve stimulation is a therapy. I didn't even talk much about that. It's pretty, it's novel and probably not one that we're going to be seeing too much. I think that this is a really good place for me to stop. Just checking ahead, excuse me. Serotonin, motor activity, and depression-related disorders. I want to make sure that we focus on that. I take a look at this and then we'll finish up with the HPA axis of major depression, which kind of goes on back to what I was talking about before. So I'm going to have a little extra segment in a subsequent video lecture. You have all of these notes in front of you, so if you just want to go ahead and skip that, that's up to you. I'm doing this to try to explain more efficiently, and I'm hoping it works at least a little bit, some of these more challenging aspects of understanding the reason that people may experience clinical depression. So I'm going to wrap this one up here, and I will be checking in with you soon with the very final segment of the clinical unipolar depression notes. And again, this is the lengthiest portion of the mental disorders, but one that I think is well worth the attention because of the prevalence that we see.